In a single-threaded software program, execution follows a strictly sequential history. You declare a variable, perform arithmetic operations in a set order, and arrive at a single, entirely predictable mathematical result. But introduce a second execution thread with simultaneous read and write access to that exact same variable, and you introduce concurrency. Two independent processes are now competing to interact with a single shared state. This diagram shows interleaving outcomes of concurrent execution. Read and write commands overlap in unpredictable sequences. If the adder writes first and is overwritten, we get outcome A. If the adder reads first, we get outcome D. The same operations yield completely different results. To restore predictable execution, software engineers apply consistency models. These establish strict ordering rules, artificially constraining the system to limit the number of possible states the execution history can enter. On a single machine, we manage this by synchronizing access to shared memory. But when we expand a database to a distributed system, that reliable shared memory disappears. Instead, we replace it with distinct physical machines communicating over highly unpredictable networks, magnifying the concurrency problem exponentially. A distributed network is a physical entity. Data travels through miles of optic fiber, copper cables, and hardware switches. It is an inherently fragile transport medium, subject to degradation, severed lines, and hardware failures. The most dangerous assumption an engineer can make is that a network is reliable. This is the first of the fallacies of distributed computing. Designing a system under the assumption that a request will always succeed leaves the architecture entirely unprepared for inevitable physical interruptions. The physics of hardware dictates strict limits. For a message to reach a remote server, it must traverse physical mediums and multiple software layers. Therefore, latency is never zero. Processing bandwidth is inherently finite, and queues overflow when consumers lag. When physical links fail entirely, the system experiences a network partition. Groups of active functioning nodes become isolated. Because they can no longer exchange messages, these independent groups proceed with execution blindly, threatening to produce conflicting results across the database. We cannot alter the physics of imperfect hardware. To maintain data integrity, engineers must construct rigorous software abstractions designed to force reliable behavior out of chaotic infrastructure. The most basic communication abstraction is the fair loss link. A process sends a message, and that message enters one of three states. It is delivered, it is delayed indefinitely, or it is irrecoverably lost in transit. The fair loss link guarantees delivery only if the sender retransmits the message infinitely. However, the sender receives zero confirmation. It has no mechanism to determine if the message arrived. We introduce sequence numbers and acknowledgements. General A sends a message. General B returns an acknowledgement. With a timeout loop, the sender retries until confirmed. But notice the return path. The acknowledgement travels the identical unreliable medium, remaining vulnerable. Retransmits solve the problem of permanent message loss, but they introduce a critical new danger. If a message succeeds but the acknowledgement fails, the sender will trigger a retransmit, resulting in message duplication. Processing duplicates destroys system integrity. If a sender retransmits a message because an acknowledgement was dropped, the receiving node processes the exact same command twice. The ideal solution to this is idempotency. An idempotent operation is one that can be executed multiple times while yielding the exact same result, without producing additional side effects on the system state. This diagram illustrates how systems simulate idempotency. Because real-world operations, like charging a customer's credit card, are inherently not idempotent, the receiving node must intercept and deduplicate the data before it executes. The receiver utilizes a reordering buffer. It checks incoming sequence numbers against a strictly maintained list of already processed messages. If a sequence number is recognized as a duplicate, it is immediately discarded. True exactly once network delivery is a mathematical impossibility over unreliable links. Distributed systems rely on at least once delivery paired with strict deduplication to create the illusion of exactly once processing. If we possess deduplicated perfect links, it seems logical we could achieve absolute state consensus across a global database. But theory dictates otherwise. The two generals problem proves that common knowledge, absolute certainty shared between independent nodes, is impossible to achieve over an asynchronous, unreliable link. General B receives the attack order and sends an acknowledgement, but B has no way to know if that acknowledgement arrived. General A must send an acknowledgement of the acknowledgement. This creates an endless chain of nested confirmations. No matter how many messages are sent, both parties remain perpetually one step away from absolute certainty. Scaling this thought experiment up to modern distributed networks leads us to the FLP impossibility theorem. The parameters of FLP impossibility state that in a purely asynchronous system, there exists no deterministic protocol capable of guaranteeing consensus in a bounded time, even if only a single remote process crashes unannounced. Without a shared clock or fixed time limits, it is mathematically impossible to distinguish between a node that has permanently crashed and a network link that is running exceptionally slow. This ambiguity prevents the system from reaching a unanimous decision state. To bypass FLP impossibility in practice, engineers introduce system synchrony. By establishing strict timing assumptions and maximum transmission delays, the system gains the ability to utilize timeouts. This enables the deployment of a failure detector. A failure detector is a local software subsystem tasked with identifying unresponsive nodes. By explicitly excluding suspected failures from the algorithm, the rest of the cluster is freed from paralysis and can safely reach consensus. Every failure detection algorithm operates on a strict trade-off between efficiency and accuracy. An algorithm that detects failures rapidly is highly efficient, but mathematically less precise. The system must constantly weigh the cost of false positives against false negatives. Wrongly marking a heavily loaded but active node as dead forces unnecessary data replication, while waiting indefinitely for a genuinely crashed node halts algorithmic progress entirely. Fixed binary timeouts are brittle in fluctuating network conditions. Modern architectures require dynamic, probabilistic methods to continuously judge a node's health without relying on arbitrary hard limits. This chart plots the mechanics of the phi accrual failure detector. Instead of treating node health as a binary up or down state, it operates on a continuous mathematical scale, dynamically calculating the probability of a process crash. The algorithm maintains a sliding window of historical heartbeat arrival times. By estimating the mean and variance of these samples, it constantly adjusts its sensitivity to match current network latency. As the time since the last heartbeat increases, the mathematical suspicion level, phi, rises until it crosses an actionable threshold. Alternatively, systems can utilize indirect verification to evaluate health, deploying the DOSIP protocol for decentralized failure detection. This matrix illustrates nodes merging heartbeat counters with random neighbors. If a timestamp fails to update, the cluster marks it failed. Crucially, this routes around direct link failures. Even if the P1-P3 connection drops, P3's timestamp propagates to P1 through P2. Gossip and phi accrual allow the system to build a highly accurate global view of failure. It achieves this without relying on any single point of observation or arbitrary timeout thresholds. In scenarios dealing with severe network partitions, some architectures deploy Fuse, a failure notification service, as a radical alternative for propagating failure states. The Fuse mechanism leverages the absence of communication. If one node stops responding to a ping, the observing node intentionally stops responding as well. This intentional cascade propagates rapidly through the cluster. It forcefully converts a single isolated process failure into a safely recognized system-wide group failure, guaranteeing all participants detect the partition. Zooming out from the specific algorithms, we can see the complete three-tiered architectural stack we've constructed to sit above the physical hardware. We mask packet loss with sequence numbers and retransmits. We simulate idempotency through reordering buffers and strict deduplication. And we bypass the mathematical impossibility of asynchronous consensus by deploying dynamic failure detection like gossip and phi accrual. Distributed database reliability depends on architecting logic that assumes constant failure and routes around it mathematically.